Hey there, Anand. Thank you so much for your question. This is a really good one, so I will run through it now. What I'd like to start with is zooming in on this diagram a little bit. I'll just make it a bit bigger. So I want to prove this, but that's not where I want to start necessarily. I want to start by figuring out, okay, what do we know in the diagram? What can we figure out? Two important things I'm seeing straight away is that there's a right angle here, a right angle here, as well as we know these two lengths. I'm also looking at it and I'm like, okay, well, in our proof, it's for y, right? Just here. But we need to include both x and theta. So if we've got to include both x and theta, we're going to have to use like this triangle and then kind of superimpose it to figure out what we'll get in the final triangle with y. And so I think the best place to start is we can actually calculate what the hypotenuse would be of this 30-degree triangle in terms of x. And we can look at that by just doing basic trig here for right angle triangles, because our hypotenuse is opposite the right angle. Actually, we'll just express it like this first. We've got here, with respect to our angle, this is the opposite side, this is the adjacent side. I might just do that in a different color. So, adjacent. And so the two kind of sides we want to work with are adjacent over hypotenuse. And if we've got adjacent over hypotenuse, that will be our cos ratio. And so what we can then do is plug in what we know. So we know that our adjacent side length is x. We want to find our hypotenuse, and we know that the angle we're referring to is 30 degrees. Now, I'm going to go ahead and assume this is tech-free. And what that means is that for our cos of 30 degrees, we've got to use our special triangles. So this would be an angle that you're expected to know in a tech-free scenario. And we can figure out what it is by using our triangle here. So this is our 30, 60, 90 triangle. If you forget how to draw it, you can just think that it's 1/2 of an equilateral triangle. An equilateral triangle will have 60 degrees in all corners. So I like to do 30 degrees at the top because you've halved it down the middle there. It's just how I like to think about it. If you prefer looking at just like a table of values for remembering exact values, that's absolutely fine as well. And so, okay, on this length, the hypotenuse, is 2. This length is 1. And this length is √3. And again there, if you forget how that's the case, if it's an equilateral triangle, all side lengths would have to start with being 2, for example, in this instance. We've then halved it at the bottom here, so this is 1. And then we've taken this kind of vertical down the middle. And so if you just remember that √3 is the side we're looking at, it always goes on that side where we've kind of cut it down the middle. Okay, so this is our special triangle. We're looking at cos of 30. So cos is going to be, again, adjacent over hypotenuse. So cos of 30 will actually give us √3 over 2. If we rearrange then, I want to find this in terms of the hypotenuse. I think the easiest way to do that is actually to flip both sides here. So I can find the reciprocal of both sides, meaning h over x equals 2 over √3. I then want to rationalize this denominator, meaning that I want the root on the top. So I'm going to multiply through by √3 over √3. Remembering this is just 1, so this doesn't actually change the fraction at all. When we do that, we get h over x equals 2 √3 on the top, and then √3 times √3 is actually just going to give you 3. And then the last thing we can do is say that, okay, well, h then, we multiply x by both sides, it has to be 2 √3 times x over 3. Awesome. So in context now, we know this side length here. Crucially, what this gives us is we can say, okay, from that information, we can now find what these side lengths are here. Okay, so once we've got our first hypotenuse, we've got enough information now to find this length here as well. And then once we've got that length, we've got enough information to find y for this other triangle. And so what this will look like then is we've kind of got the same scenario we had down here, except a different angle. And so the side we're trying to find, this blue one, is actually the hypotenuse here. I'm going to make it a different letter. We'll say L for length. So L is the hypotenuse. In relation to the angle, this H value we found, our first hypotenuse, is now the opposite side. And so the ratio we're trying to compare is opposite over hypotenuse. And this is going to be our sine ratio. So this is for triangle 2. Triangle 2. All right, so we know our angle of reference here is 60 degrees. We also know that our opposite side is what we found just before. So 2 root 3 times x over 3. That then, I'm just going to write that in brackets and use just an old-fashioned division sign, divided by L. And then that's equaling sine of 60 degrees. We can come back to our triangle here and figure out that sine of 60 degrees is actually going to be the exact same ratio, because we go opposite over hypotenuse. So it too is root 3 on 2, which is pretty helpful here. So we've got 2 root 3 x over 3 times 1 on L equals root 3 on 2. And this is pretty cool now. We can actually cancel some terms here. Yeah, so if we divide both sides by root 3, sorry, not times, we divide by root 3. We can cancel out all of these terms. Like that, like that, yeah, like that. So that helps us, and then we can write out our mu equation, which will be 2/3 x, or even, actually I'll keep it like that for now, just equals a half. So that's cool. What I want to try and do now, we got to rescue this L. It's kind of trapped underneath here. We need to isolate it. There's a few options here. We could look at doing the reciprocal again, but what I might start with first is actually multiplying both sides by this entire component. So what that'll look like is 3 over 2x multiplied by everything. It's going to cancel on this side. So then we get 3 over 2x on the right-hand side. That comes out to, okay, 1 on L equals 3 over 4x. And now we can do what we did up here and flip both sides, which gives us L equals 4x over 3. Perfect. And now finally, we are at the point where we can look at our final triangle. Okay, so for our final triangle, what we're going to use is the sine rule. And it looks a little bit cryptic here, a little bit, but what it means essentially is when we've got side A over sine of the angle A, that refers to angles that are opposite a side. So for example, you could think of y here as side A, and then theta here as angle theta. Sorry, theta here is angle A. Similarly, we can think of 45 as angle B and L as side B. What that then gives us is a nice ratio that we can then solve. So it will be L over sine of 45 equals y over sine of theta. And now we should have enough information to rearrange to get to our actual proof. All right, so doing a little bit of simplification work here. I just want to start by actually getting y by itself. And that will, because in our actual proof, we want y just by itself on one side. So I'm going to multiply both sides by this sine of theta. That will get us y equals L sine theta over sine 45. This sine 45 component we can actually solve for. It's a similar method to up here with tech-free solutions. Different triangle though. What that one's going to look like is 90-degree triangle, 45 in here, 45 in here, and then it's going to be 1, 1, root 2 as your ratio. And so if we're looking at the sine of 45, that's opposite over adjacent, opposite over hypotenuse. So sine of 45 is going to be 1 on root 2. And I find it confusing when I've got like a fraction within a fraction. So I actually like doing it just old school division sign instead of this line here, divided by sine of 45, which is 1 on root 2. The other thing I can do at this point is then sub in L, and that's going to be 4x over 3 times sine of theta divided by 1 on root 2. When we divide by a fraction, we can multiply by its reciprocal. And so 4x over 3 times sine of theta comes multiplied by just root 2 on 1, which gets us y equals 4 root 2 times x times sine of theta over 3, which I believe was what we were required to prove. Cool. So essentially there we've just applied a couple of understandings around manipulating our just basic trig ratios, so sine, cos, and tan, except in a more complex scenario because we've now got to build up to kind of get this length. Then once we've got that length, we're applying the sine rule to figure out a relationship between side and angle that uses the information we already have. Yeah, so thanks for submitting that question. Hopefully that was a bit helpful for you or not. Really appreciate the support, and yeah, if you enjoyed, feel free to like the video. That'd really help us out. And don't hesitate to ask us more questions in the future. Thanks so much.